Welcome to this video. My name is Mark Scythian. The date today is July 28, 2024, and the title of this video is Conservation of Energy. So this is a concept consistent with the first law of thermodynamics, which simply states that energy cannot be created or destroyed, but only changed in form. So what that means is that we have to first define what energy is. Energy is the capacity to perform physical work. So of course we could break that down into energy at rest, potential energy, and energy in motion, kinetic energy. But we'll start with an example. There's infinite examples to describe the conservation of energy, but we'll start with a relatively practical example focusing on electrodynamics. So this is electrical energy converted to any other form of energy. So just a really practical example is electrical power converted to mechanical power, of course minus the efficiency losses. So a device which does just that is the electric motor. The electrical power goes in, minus efficiency losses, and then the mechanical power comes out. And so the voltage that goes into that electric motor converts to the RPM in the motor. So it's quote unquote like an electrical velocity is the voltage. And the current, how much or how many electrons go through that circuit, the cross-sectional area of the wiring would be the current or amperes. So that's the quote-unquote electrical pressure that converts into the torque at the motor. So if we wanted to just know the actual available horsepower output of the motor or an engine, it is the RPM times the foot-pounds torque times the number of radians in one rotation, 360 degrees, so 2 pi or 6.28 radians, then divided into 33,000 foot-pounds per minute, because we're dealing with RPM rather than revolutions per second. We're doing RPM as in the revolutions per minute. 550 foot-pounds per second is the mechanical power of 1 horsepower times 60 seconds, so 33,000. So the product of the voltage and the current in a DC circuit for a DC electrical motor will result in the watts electrical power, and in this case delivered into the electric motor. So that splits across the voltage becoming the RPM and the current, how much electricity converting to the electric motor's torque. So the energy has neither been created or destroyed, it just changes in form. Okay, this next example is electro-acoustics. This is electrical power converted into sound. So the voltage that goes into the amplifier converts to the sound wave frequency, so how many cycles per second, minus the efficiency losses, of course, and then the current that goes into the amplifier converts into the sound wave amplitude, or the peaks and valleys, or the crests and troughs of the wave, how high and low the amplitudes will project. So that then translates into the volume, or how loud sound is. That's a function of the current. So the increased voltage then shortens the wavelengths and allows a higher frequency, more cycles per second. And so the increased voltage will increase the sound wave frequency, increased current, or amps, increased amplitude. And of course, if we have a product of these two, then we just have greater intensity of sound. But most importantly, the energy is neither created nor destroyed. So we could measure the sound intensity in a derivative of watts power sound divided into a unit of area, square meters, and its logarithmic calculation, base 10 log, would be in the decibels sound intensity. So the sound wave speed, unlike an electromagnetic wave, we have a constant speed with electromagnetic waves like gamma, radio waves, microwaves, etc. But a mechanical wave such as sound projecting or emitting through some substance like the air or water or a gas have a speed equal to their wavelength times the frequency. So the sound wave speed may change through actually the sound wave speed does change through different mediums, but when we refer to sound, we're usually referring to the sound wave through air or the atmosphere. Next is electro-thermal, and this is just simply a electric heating element. So the voltage will govern how fast the heating element heats up. The current will determine how much mass, including the heating element, can practically reach the rated temperature. So this would be the electrical mass becoming the thermal mass, and the voltage is the speed of the electrical flow, practically speaking, and that is how fast the element heats up. So if you have a high voltage heating element, it's going to heat up relatively faster than a low voltage heating element, and the current is again the mass of the heating element and whatever it's heating. So if it's a high current, then it's going to be able to increase the temperature of a much larger mass. Next we have electro-hydraulic. So again, that is an electrical power source delivered into an electric motor, which then powers a hydraulic pump and then delivers the fluid power. And so the voltage that goes into that electric motor will govern the RPM of the electric motor, and thus the fluid velocity through the hydraulic line. And the current will again govern the torque of the electric motor, and then thus the fluid pressure in the line, in the hydraulic line. Next we have electroluminescence. This is the conversion of electricity into light. And so the voltage will govern the light range, how far the light projects, and the current will be the width or the domain of the light emission. So if we have both high voltage, high current, we have a range that is increased and a domain that is increased as well. But again, we have not created or destroyed the energy, the electrical energy. We just converted it into another form of energy, or in this case, luminescence energy, light energy, with some efficiency losses. So if we were dealing with electricity as the source of the the electrical power as the source energy of the mechanical, thermal, sound, hydraulic, pneumatic power, then there really is no difference between these energies. It's just that understanding the behavior of electricity either in series or parallel circuits or the principle of voltage drops or current draws, depending if the circuit is series or parallel or both. And then of course we have either AC or DC electrical power. So one is direct rectified bridge current from positive to negative, the DC, and the AC is alternating current and voltage, sinusoidal or sine waves, oscillating or alternating back and forth. So if we're dealing with just DC electrical power, then we are concerned with the resistance, or Ohm's law, which is the resistance times the current will yield the voltage. But if we're dealing with AC electrical power, then we're dealing with impedance, which is the effective voltage divided into the effective current to then get the Z value, or the impedance. So these correlate with heat or efficiency loss. So if you calculated the resistance in a DC circuit, it would correlate also to the heat that builds up through the device and the friction that's left over. It would mathematically transduct out of that resistance. So you'd have one electrical correlation mirroring the physical heat and efficiency losses and friction. So that's how electronic sensing can accurately understand the mechanical and structural performance of, let's say, an electric motor based on how much heat is building up in the motor, and then whatever's left is the friction at the bearings and the moving parts, etc. And so other things like lubrication and its status on percentage scales can also be isolated, because if we're getting more friction with, let's say, oil degradation, we definitely would know that the molecular structure is compromised or compromising, and it would actually correlate to an electrical mirror of that friction increase. So you'd have a slightly higher resistance, but then again you'd have a system that corrects on its own, not altering the power input. So why this is important is that all of these different functions on the electrical, mechanical, thermal, hydraulic, pneumatic, sound, light, they're all one and the same, but they're set up in equivalence. So once you have the wattage value, you can calculate the foot-pounds per second, the BTU per second. You can calculate all the other energy and power applications directly, not only to power these systems from electricity or electrical power, but to also get the performance factors as well. The system, the electronic and electrical sensing is also a function of this. So all of these things, even instrumentation, are transfer of power, conservation of energy. So resistance or impedance, depending if DC or AC electrical power, correlates with heat or efficiency loss, excluding power regulation by means of digital pulse width modulator. So PWM is something like an adjustable resistor or a potentiometer, except instead of dissipating the power or dissipating the voltage or the current into heat to incur the voltage or current drops in a series or parallel circuit, instead it'll send the excess voltage or current, depending on the type of circuit, series or parallel, back to the source. So this PWMs can be programmed completely informationally, and the data stream that is programmed into it, the software, will have the same effect as a hardware component, but it doesn't have to be physical. So there's a lot of things you could do with a PWM, and so therefore all of these could be scaled down based on equivalent power. So if we had excessive heat or friction, maybe the oil schedule is nearing its service limit. Things like voltage could go up, current could go down to stabilize that resistance to its normal level. And you can do things like that without paying, without having without having to power that deficiency. Otherwise, you'd have to just throw all of the voltage and current in and dissipate it into heat. And of course it would work, but it would not be as efficient throughout the entire system itself. But with a PWM, you could actually upgrade the voltage, downgrade the current to stabilize that resistance, and just throw that excess voltage and current back to the source without any power penalties. What I was meaning to say, there's a little bit of power that's penalized when you have a bit of wear, and the PWMs make power systems or devices very efficient and very, very reliable. So in case you are nearing a maintenance schedule, or you're past your maintenance schedule, the PWM can kind of calibrate the input voltage and current so that the impedance or resistance can be stabilized, and this makes the reliability go up. So many people don't take care of their devices, but they kind of get away with the reliability, but eventually other systems start to go, and then you have much more power consumption elsewhere, and then eventually that costs them more, so they do something about it. And sometimes it's just a regular servicing that puts all this back into normal specifications, and things like PWMs make that so practical. So I just wanted to bring that up. This is not an electronics lecture. There's other videos in my YouTube library that cover these concepts, but the whole overview is that all of this technology is reliable because we know we cannot create or destroy energy. We can only convert it into another form. So that energy could also be instrumentation. It could be sensing, it could be detection. It isn't just electric, it isn't just the mechanical power or the hydraulic power. It could also be the data power, the sensor power. These are all costing small amounts of power as well. And the energy per unit of time then becomes power. But if we're just measuring energy in the form of foot-pounds or Newton meters, i.e. joules, then we have a metric that we can keep consistent, making the potential and kinetic energy equalize. But when we start to discharge it and use it into power, we have to take that foot-pounds and divide it into time, foot-pounds per second, or the joules per second. So 1 foot-pound is 1.36 joules. And if we release a joule per second, then we have a watt. But then if we have 1 foot-pound per second would be what would correlate to 550 foot-pounds per second total horsepower. But we could also translate that to 0.737 foot-pounds per second to a watt as well. So these are all relative, and when we have a component we're working with, we have to find its equivalent somewhere else, and we can do so when we realize it's all conservation of energy, or energy cannot be created or destroyed, but only changed in form. And so the last example here is chemical potential energy converted to electrical kinetic energy. So this is chemical potential energy. This is like gasoline in a tank, and then it powers a piston engine, which then powers an AC electrical generator. And then we use the generator, we get electrical kinetic energy. So in this case, 0.1 pounds mass per second of gasoline is being burnt or consumed. There is 20,000 BTUs per pound energy density regarding gasoline. So 1 pound of gasoline has 20,000 BTUs of potential energy, and there is 6 pounds per 1 US liquid gallon volume. So there's 120,000 BTUs per US gallon of gasoline. So if we're consuming 0.1 pounds per second gasoline into the piston engine, then we can multiply the 0.1 times 20,000 to get 2,000 BTUs per second heat going into the engine. And then we know that piston engines have 30% brake thermal efficiency, meaning that it will cost 70% of the fuel's energy to keep the engine running, to power it, but then whatever's left that we can use to move the car or drive the generator, overcome aerodynamic drag, tire rolling resistance, etc., is 30%. So we take 2,000 times 0.3, 600 BTUs per second of equivalent mechanical power. So that's in a thermal metric, and we know that 1056 watts is the amount of power equal to 1 BTU per second. So we can take the 600 and multiply it times 1056. So the mechanical power output that we can use at the crankshaft going to the AC generator is 633,600 watts of mechanical power that is driving the AC electrical generator. Most AC electrical generators are 85% efficient. So this then gives us 538,560 watts of AC true power, or AC electrical true power. So 538.6 kilowatts of AC electrical true power is harnessed by burning 0.1 pounds per second of gasoline, which is a lot of gasoline actually, because after 10 seconds we burnt an entire pound, and that's 1/6 of a gallon. So it would only take 1 minute to burn a whole gallon of gasoline in this giant piston engine. So obviously it's rated at, this would be 600. This would be like a 850 brake horsepower piston engine being powered on 0.1 pounds per second gasoline consumption, and that would take 1 minute to burn an entire gallon. But the result is you get 538.6 kilowatts of AC electrical true power, which is a lot of power. Power an entire neighborhood off this one engine. Okay, so 0.1 pounds mass per second gasoline combustion, or 2,000 times 1056. So we got 2.112 million watts of gasoline combustion heat going into the engine, and then it converts it to 30% of that in mechanical power out of the engine to then drive the AC electrical generator, which only loses 15% efficiency, to then yield 538.6 or 538.56 kilowatts AC electrical true power. So the overall efficiency is the output, final output of 538.56 kilowatts of AC electrical power divided into the equivalent wattage of combustion burning 0.1 pounds per second of gasoline. So that's 2.112 million watts. So you have about the typical overall efficiency of such a system, right around 25.5 to 26% overall efficiency. 74.5% of that potential energy in the gasoline is lost to power the equipment. So we have to power the equipment, and then whatever is left more than the energy needed to power the equipment is then the useful power output. And in this case it is almost 75% of the potential energy of the fuel is used to just power the engine, and then 25% we get to keep in the form of the electrical power output. So the main takeaway in all of this is that energy is neither created nor destroyed, but it's only changed in form. So this is what the conservation of energy is all about. And in another lecture, I can cover the second law of thermodynamics, entropy, and the third law, which is most practically reaching the zero entropy state. And it is quite clear, but it is a bit abstract. And then, of course, we have the zeroth law of thermodynamics, which has a little bit more to do with the quantum side of superpositioning, but it has more to do with an absolute theoretical zero absolute temperature. So at least in theory, it is something that makes the quantum applications highly practical, but not even outer space is at absolute zero. So they've come very, 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 very close to artificially creating absolute zero, but there are some wonders and some extreme hazards of doing just that, to artificially create zero absolute temperature. So we'll cover those on a different lecture, but this lecture is about the conservation of energy, and that we're not creating or destroying energy, we're just changing it in form. Thank you for watching this video, and have a great day.